Alright, hello everyone, welcome back. Today we are going to learn the exponential growth and decay. I have no idea what it is, but let me get into it.
In this video, I want to introduce you to the idea of an exponential function, and really just show you how fast these things can grow. So let's just write an example exponential function here. So let's say we have y is equal to 3 to the x power. Notice this isn't x to the third power. This is 3 to the x power. Our independent variable x is the actual exponent. So let's make a table here to see how quickly this thing grows. And maybe we'll graph it as well. So let's take some x values here. So let's start with x is equal to -4. Then we'll go to -3, -2, 0, 1, 2, 3, and 4. And let's figure out what our y values are going to be for each of these x values. Now, here y is going to be 3 to the -4 power, which is equal to 1 over 3 to the 4th power. 3 to the third is 27 times 3 again is 81. So this is equal to 1 over 81. When x is equal to -3, y is 3. Let me do this in a different color. That color is hard to read. Y is 3 to the -3 power. Well, that's 1 over 3 to the third power, which is equal to 1 over 27. So we're going from a super small number to a less super small number. And then 3 to the -2 power is going to be 1 over 9, right? 1 over 3 squared. And then we have 3 to the 0 power, 3 to the 0, which is just equal to 1. So we're getting a little bit larger, but we're going to see we're about to explode. Now we have 3 to the first power. That's equal to 3. Then we have 3 to the second power, right? Y is equal to 3 to the second power. That's 9. 3 to the third power, 27. 3 to the fourth power, 81. If we were to put the fifth power, 243. Let's graph this just to get an idea of how quickly we're exploding. So let me draw my axes here. Draw my axes. So that's my x-axis, and that is my y-axis. That is my y-axis. And let me just do it in increments of 5, because I really want to get the general shape of the graph here. So let me just draw as straight a line as I can. And let's say this is 5, 10, 15. Actually, I won't get to 81 that way. I want to get to 81. Actually, well, that's good enough. Let me draw it a little bit differently than I've drawn it. So let me draw it down here, because all of these values, you might notice, are positive values because I have a positive base. So let me draw it like this, like that. Good enough. And then let's say I have 10, 20, 30, 40, 50, 60, 70, 80. That is 80 right there. That's 10. That's 30. That'll be good for approximation. And then let's say that this is -5. This is +5 right here. And actually, let me stretch it out a little bit. Say this is -1, -2, -3, -4. And then we have 1, 2, 3, and 4. So when x is equal to 0, we're equal to 1, right? When x is equal to 0, y is equal to 1, which is right, maybe right around there. When x is equal to 1, y is equal to 3, which is maybe right around there. When x is equal to 2, y is equal to 9, which is right around there. When x is equal to 3, y is equal to 27, which is right around there. When x is equal to 4, y is equal to 81. Y is equal to 81. So you see very quickly this is just exploding. If I did 5, it'd go to 243, which wouldn't even fit on my screen. When you go to -1, we get smaller and smaller. So at -1, we're at 1/9. I mean, eventually you're not even going to see this. It's going to get closer and closer to 0. As this approaches larger and larger negative numbers, or I guess I should say smaller negative numbers. So 3 to the -1,000, 3 to the -1,000,000. We're getting numbers closer and closer to 0 without actually ever approaching 0. So as we go from -infinity, x is equal to -infinity, we're getting very close to 0. We're slowly getting ourselves away from 0. But then, bam, once we start getting into the positive numbers, we just explode. We just explode, and we keep exploding at an ever increasing rate. So the idea here is just to show you that exponential functions are really, really dramatic, that they're the kind of, well, you can always construct a faster expanding function. For example, you could say y is equal to x to the x, even faster expanding. But out of the ones that we deal with in everyday lives, this is one of the fastest. So given that, let's do some word problems that just give us an appreciation for exponential functions. So let's say that someone sends out a chain letter on, let's say in week 1. Week 1, someone sends a chain letter to 10 people. To 10 people. And the chain letter says you have to now send this chain letter to 10 more new people, and if you don't, you're going to have bad luck and your hair is going to fall out and you'll marry a frog or whatever else. So all of these people agree, and they go and each send it to 10 people the next week. So in week 2, they go out and each send it to 10 more people. So each of those original 10 people are each sending out 10 more of the letters. So now 100 people have the letters, right? Each of those 10 sent out 10. So that 100 letters were sent out. So let me see. Sent. 10 were sent. Here, 100 were sent. In week 3, what's going to happen? Each of those 100 people who got this one, they are each going to send out 10, assuming that everyone is really into chain letters. So 1,000 people are going to get it. And so the general pattern here is the people who receive it. So in week n, right, where n is the week we're talking about, how many people receive the letter? In week n, we have 10 to the nth people receive I before e except after c. Receive the letter. So if I were to ask you how many people are getting the letter on the 6th week, on the 6th week, how many people are actually going to receive that letter? Well, what's 10 to the 6th power? 10 to the 6th is equal to 1 with 6 zeros, which is 1,000,000 people are going to receive that letter in just 6 weeks, just sending out 10 letters each. And obviously in the real world, most people chuck these in the basket, so you don't have this good of a hit rate. But if you did, if every 10 people you sent it to also sent it to 10 people, and so on and so forth, by the 6th week, you would have 1,000,000 people. And by the 9th week, you would have 1,000,000,000 people.
All right. This method or this explanation told us that how some technical company use this strategy to increase their users, the number of their users. Well, they simply does the same thing here, which is, for example, at first they got 10 people to promote their to promote their product, and then the 10 people somehow each one again send out promote 10 times for 10 different people for their products, and by doing so they could achieve a really great achievement, which is increase their user numbers in a very short time, for example a few weeks or just 2 or 3 months. And if you are a Chinese, I could just tell you the company name. It's called Pinduoduo. That's how they use this strategy to increase their users' number.
So I have 2 different XY relationships being described here. And what I would like to do in this video is figure out whether each of these relationships, whether they are either linear relationships, exponential relationships, or neither. And like always, pause this video and see if you can figure it out yourself. So let's look at this first relationship right over here. And the key way to tell whether we're dealing with a linear or exponential or neither relationship is think about, okay, for a given change in x, and you see each time here we are increasing x by the same amount. So we're increasing x by 3. So given that we are increasing x by a constant amount, by 3 each time, does y increase by a constant amount, in which case we would be dealing with a linear relationship? Or is there a constant ratio between successive terms when you increase x by a constant amount, in which case we would be dealing with an exponential relationship? So let's see. Here we're going from -2 to 5. So we are adding 7. When x increases by 3, y increases by 7. When x is increasing by 3, y increases by 7 again. When x increases by 3, y increases by 7 again. So here it is clearly a linear relationship. Linear relationship. In fact, you can even You could even plot this on a line if you assume that these are samples on a line. You could think even about the slope of that line. For a change in x, for a given change in x, the change in y is always constant. When our change in x is 3, our change in y is always 7. So this is clearly a linear relationship. Now let's look at this one. Let's see. Looks like our x's are changing by 1 each time. So plus 1. Now what are y's changing by? Here it changes by 2. Then it changes by 6. All right, it's clearly not linear. Then it changes by 18. Clearly not a linear relationship. If this was linear, these would be the same amount, same deltas, same change in y for every time because we have the same change in x. So let's test to see if it's exponential. If it's an exponential, for each of these constant changes in x's, when we increase x by 1 every time, our ratio of successive y should be the same. Or another way to think about it is, what are we multiplying y by? So to go from 1 to 3, you multiply by 3. To go from 3 to 9, you multiply by 3. To go from 9 to 27, you multiply by 3. So in a situation where every time you increase x by a fixed amount, in this case 1, and the corresponding y's get multiplied by some fixed amount, then you are dealing with an exponential relationship. Exponential relationship right over here.
Okay, that could be very clear. If we are dealing with a linear relationship, then for the result, each time it will increase for a fixed amount. And you will use the operator like plus or minus. Well, if you are dealing with an exponential relationship, then the result y, what you're gonna do to it is to use the multiplication operator, this one, or divide operator.
You put $3,800 in a savings account. The bank will provide 1.8% interest on the money in the account every year. Another way of saying that, the money in the savings account will grow by 1.8% per year. Write an expression that describes how much money will be in the account in 15 years. So let's just think about this a little bit. Let's just think about the starting amount. So in the start, we're just going to put $3,800. We could view that as year 0. Actually, let me write it that way. So the start is the same thing as year 0. And we're going to start with $3,800. Now let's think about year 1. How much money will we have after 1 year? Well, we would have the original amount that we put, $3,800. And then we're going to get the amount that we get in interest. And they say that the bank will provide 1.8% interest on the money in the account. So it'll be plus 1.8% times 3,800. Our $3,800 or our $3,800. And we could also write this as a decimal. This is equal to 3,800 plus, and I'll switch the order of multiplication here, plus 3,800 times 0.018. 1.8% is the same thing as 18 thousandths or 1.8 hundredths, depending on how you want to pronounce it. And so here you might say, well, there's kind of an interesting potential simplification mathematically here. I could factor 3,800 out of each of these terms. I have a 3,800 here, I have a 3,800 here, so why don't I factor it out, essentially undistributed it. So this is going to be 3,800 times, when you factor it out here, you get a 1, plus, when you factor it out here, you get 0.018. And so I could just rewrite this as 3,800 times 1.018. So this is an interesting time to pause. We're not at the full answer yet, how much we have in 15 years, but we have an interesting expression for how much we have after 1 year. Notice that if the money is growing by 1.8%, or another way, it was growing by 0.018, that's equivalent to multiplying the amount that we started the year with by 1 plus the amount that it's growing by, or 1.018. And once again, why does this make intuitive sense? Because at the end of the year, you're going to have the original amount that you put, that's what that 1 really represents, and then plus you're going to have the amount that you grew by. So you multiply both the sum here times the original amount you put, and that's how much you'll have at the end of year 1. What about year 2? So year 2. Well, we know what we're going to start with in year 2. We're going to start with whatever we finished year 1 with. So we're going to start with 3,800 times 1.018. But then it's going to grow by 1.8%, or grow by 0.018. And we already said if you're going to grow by that amount, that's equivalent to multiplying it by 1.018. Well, this is the same thing as 3,800 times 1.018 to the second power. I think you see where this is going. Every time we grow by 1.8%, we're going to multiply by 1.018. And if we're thinking about 15 years in the future, we're going to do that 15 times. So 1 year in the future, your exponent here is essentially 1. 2 years, your exponent is 2. So year 15, I can just cut to the chase here. So year 15, well, that's just going to be, we're going to have the original amount that we invested, and we are going to grow 1.018 15 times. So we're going to multiply by this amount 15 times to get the final amount. And one of the fun things, this is actually called compound growth, where every year you grow on top of the amount that you had before. You'll see if you type this into a calculator that even though 1.8% per year does not seem like a lot, over 15 years, it actually would amount to a reasonable amount. But this is the expression. They're not asking us to calculate it. They just want us to know an expression that describes how much money will be in the account in 15 years.
All right, this is quite useful. For example, if you want to know how much money you will get from a bank that you choose, right? You just have to write an expression and put the years into that expression, and it's done. You would know how much money you would get by that years.
We're asked to graph y is equal to 5 to the xth power. And we'll just do this the most basic way. We'll just try out some values for x and see what we get for y, and then we'll plot those coordinates. So let's try some negative and some positive values, and I'll try to center them around 0. So this will be my x values, this will be my y values. Let's start first with something reasonably negative, but not too negative. So let's say we start with x is equal to negative 2. Then y is equal to 5 to the x power, or 5 to the negative 2 power, which we know is the same thing as 1 over 5 to the positive 2 power, which is just 1/25. Now let's try another value. What happens when x is equal to negative 1? Then y is 5 to the negative 1 power, which is the same thing as 1 over 5 to the first power, or just 1/5. Now let's think about when x is equal to 0. Then y is going to be equal to 5 to the 0th power, which we know anything to the 0th power is going to be equal to 1. So this is going to be equal to 1. And then finally we have, well, actually let's try a couple of more points here. Let's try out, let me extend this table a little bit further. Let's try out x is equal to 1. Then y is 5 to the first power, which is just equal to 5. Let's do one last value over here. Let's see what happens when x is equal to 2. Then y is 5 squared, 5 to the second power, which is just equal to 25. And now we can plot it to see how this actually looks. So let me get some graph paper going here. My x's go as low as negative 2, as high as positive 2, and then my y's go all the way from 1/25 all the way to 25. So let me So I have positive values over here. So let me draw it like this. So this could be my x-axis. That could be my x-axis. And then let's make this my y-axis. Draw it as neatly as I can. So let's make that my y-axis. And my x values, this could be -2. Actually, make my y-axis keep going. So that's y. This is x. That's -2. That's -1. That's 0. That is 1. And that is +2. And let's plot the points. X is -2. Y is 1/25. Actually, let me make the scale on the y-axis. So let's make this. So we're going to go all the way to 25. So let's say that this is 5. Actually, I have to do a little bit smaller than that, too. So this is going to be 5, 10, 15, 20, and then 25 would be right where I wrote the y, give or take. So now let's plot them. -2, 1/25. -2, 1/25. 1 is going to be like there. So 1/25 is going to be really, really close to the x-axis. That's about 1/25. So that is -2, 1/25. It's not going to be on the x-axis. 1/25 is obviously greater than 0. It's going to be really, 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 really close. Now let's do this point here in orange. -1, 1/5. -1/5. 1/5 on this scale is still pretty close. It's pretty close. So that right over there is -1, 1/5. And now in blue, we have 0, 1. 0, 1 is going to be right about there. If this is 2.5, that looks about right for 1. And then we have 1, 5. 1, 5 puts us right over there. And then finally we have 2, 25. When x is 2, y is 25. 2, 25 puts us right about there. And so I think you see what happens with this function, with this graph. It starts off, the further negative in the negative x, the further in the negative direction we go, 5 to ever increasing negative powers gets us closer and closer to 0, but never quite. So we're leaving 0, getting slightly further from 0. Right at the y-axis, we have y equal 1. And then once the exponent over here, or right at x is equal to 0, we have y is equal to 1. And then once x starts increasing beyond 0, then we start seeing what the exponential is good at, which is just this very rapid increase. Some people would call it an exponential increase, which is obviously the case right over here. So then if I just keep this curve going, you see it's just going on kind of this, sometimes called a hockey stick. It just keeps on going up like this at a super fast rate, ever increasing rate. So you could keep going forever to the left and you get closer and closer and closer to 0 without quite getting to 0. So 5 to the negative billionth power is still not going to get you to 0, but it's going to get you pretty darn close to 0. But obviously if you go to 5 to the positive billionth power, you're going to get to a super huge number because this thing is just going to keep skyrocketing up like that. So let me just draw the whole curve, just make sure you see it. Over here, I'm not actually on 0, although the way I drew it, it might look like that. I'm slightly above 0. I'm increasing above that, increasing above that. As once I get into the positive x's, then I start really, really shooting up.
All right, so printing out the graph is quite simple and easy. All you have to do is to find out a bunch of x and y value and print out into your graph. Then you connect each points together. Then you'll get the graph that you want. And to be honest, for this graph, it's one type of machine learning activation function. They are the same thing, as I think. The good part about learning the mathematics is that you can always find something useful in it. For example, you could find, oh, this part of knowledge is used in, for example, programming, or this part of knowledge was used in physicals or chemicals or biologic or whatever field that you may know, because the maths are in everywhere in your life, but most people do not say it.
What we're going to do in this video is quickly review exponential growth and then use that as our platform to introduce ourselves to exponential decay. So let's review exponential growth. let's say we have something that, and I'll do this on a table here. Oops, let me make that straight. So let's say this is our x and this is our y. And let's say when x is 0, y is equal to 3. And every time we increase x by 1, we double y. So y is going to go from 3 to 6. If x increases by 1 again, so we go to 2, then we're going to double y again. And so 6 times 2 is 12. This right over here is exponential growth. And you could even go for negative x's. When x is negative 1, well, if we're going back 1 in x, we would divide by 2. So this is going to be 3 halves. 3 halves. And notice, if you go from negative 1 to 0, once again, you keep multiplying by 2. And this will keep on happening. And you can describe this with an equation. You could say that y is equal to, and sometimes people might call this your y-intercept or your initial value, is equal to 3. Essentially, what happens when x equals 0 is equal to 3 times our common ratio. And our common ratio is, well, what are we multiplying by every time we increase x by 1? So 3 times our common ratio 2 to the x power. And you can verify that. Pick any of these. When x is equal to 2, it's going to be 3 times 2 squared, which is 3 times 4, which is indeed equal to 12. And we can see that on a graph. So let me draw a quick graph right over here. So I'm having trouble drawing a straight line. All right, there we go. And let's see. We could go, and then they're going to be on a slightly different scale, my x and y axes. So this is x-axis, y-axis, and we go from negative 1 to 1 to 2. And let's see, we're going all the way up to 12. So let's say that this is 3, 6, 9, and let's say this is 12. And we could just plot these points here. When x is negative 1, y is 3 halves. So it looks like that. Then at y equals 0, when x is 0, y is 3. When x equals 1, y has doubled. It's now at 6. When x is equal to 2, y is 12. And you will see this telltale curve. And so there's a couple of key features that we've already talked about several of them. But if you go to increasingly negative x values, you will asymptote towards the x-axis. It'll never quite get to 0 as you get to more and more negative values, but it'll definitely approach it. And as you get to more and more positive values, it just kind of skyrockets up. We've talked about in previous videos how this will pass up any linear function or any linear graph eventually. Now, let's compare that to exponential decay. Exponential decay. And an easy way to think about it, instead of growing every time you're increasing x, you're going to shrink by a certain amount. You are going to decay. So let's set up another table here with x and y values. That was really a very, this is supposed to, when I press shift, it should create a straight line, but my computer, I've been eating next to my computer. Maybe there's crumbs in the keyboard or something. All right, so here we go. We have x and we have y. And so let's start with, let's say we start in the same place. So when x is 0, y is 3. But instead of doubling every time we increase x by 1, let's go by half every time we increase x by 1. So when x is equal to 1, we're going to multiply by 1/2, and so we're going to get to 3 halves. And then when x is equal to 2, we'll multiply by 1/2 again, and so we're going to get to 3 3/4, and so on and so forth. And if we were to go to negative values, when x is equal to -1, well, if we're going backwards in x by 1, we would divide by 1/2, and so we would get to 6. Or going from -1 to 0, as we increase x by 1, once again, we're multiplying by 1/2. And so how would we write this as an equation? I encourage you to pause the video and see if you can write it in a similar way. Well, it's going to look something like this. It's going to be y is equal to, you could have your y-intercept here, the value of y when x is equal to 0, so it's 3, times, what's our common ratio now? Well, every time we increase x by 1, we're multiplying by 1/2. So 1/2, and we're going to raise that to the x power. And so notice, these are both exponentials. We have some, you could say, y-intercept or initial value, and it's being multiplied by some common ratio to the power x. Some common ratio to the power x. But notice, when you're growing, our common ratio, and it actually turns out to be a general idea, when you're growing, your common ratio, the absolute value of your common ratio, is going to be greater than 1. Let me write it then. So the absolute value of 2 in this case is greater than 1. But when you're shrinking, the absolute value of it is less than 1. And that makes sense, because if you have something where the absolute value is less than 1, like 1/2 or 3/4 or 0.9, every time you multiply it, you're going to get a lower and lower and lower value. And you can actually see that in a graph. Let's graph the same information right over here. And let me do it in a...
Alright, to be honest, we do not have to dig deep into it because it's quite simple. If the multiply number you have is greater than 1, that means for each multiplication, your old number would be, or the result you get would be greater than your previous number. That's for sure, because the factor is greater than 1. But if you have a factor that's less than 1, then for each time the new result would be definitely smaller than the previous one. That makes sense. So for the first case, if your factor is greater than 1, it will be a growth function. But if you have a factor less than 1, you would have a decay function. Yeah, that makes sense. So that's it.
The number of branches of an oak tree and a birch tree since 1950 are represented by the following tables. So for the oak tree, we see when time equals 0 it has 34 branches. After 3 years, it has 46 branches, so on and so forth. And then the birch tree, they give us similar data. At the beginning, has 8 branches. In 10 years, has 33 branches, and they give us all of that. And what I want to think about in this video is, how should we model these? If we want to model these with functions, and the choices we'll give ourselves, there are other options, but the choices we'll give ourselves in this video are linear and linear versus exponential functions. Which of these are going to be better for modeling this data? So let's first look at the oak tree. And the key to realization is whenever I have a fixed increase in time, so each of these steps, this is plus 3 years. So it's a fixed increase in time. What happens to my number of branches? Is it going to be a fixed change, or roughly a fixed change, in which case a linear model might be good? Or is it going to be a change that's dependent on where we were? So what am I talking about? So 34 to 46, that is plus 12. 46 to 59 is plus 13. 59 to 70 is plus 11. 70 to 82 is plus 12. And so at first you might say, well, hey, this isn't an exactly fixed change. These numbers, they seem to average right around 12. But when you're looking at real-world data, you're never going to get something that is exact. The models are just going to give us a good fit, are going to give us a good approximation of the behavior of the number of branches over time. For me, this is pretty close to a constant 12 branches a year. So I would construct a linear model here. I would say here, branches as a function of time. Now, let me be clear. This isn't 12 branches per year. This is 12 branches every 3 years. This was 13 branches over 3 years. This was 11 branches every 3 years. But we're going to average 12 branches over 3 years. So the number of branches we have, we're going to start at 34 branches. And then minus, if we have 12 branches every 3 years, that's 4 branches every, or I should say plus, 4 branches every year. And you could test this out. B of 0 is going to give us 34 branches. B of 12, let's just really test out the extreme part of the model. B of 12 is going to be 34 plus 48, which is equal to 82. So this model works quite well. It's going to have a couple of places where it's not exactly fitting the data, but it fits it quite well. And so this is a linear model. So this one is linear. Now let's look at the birch tree. So time equals 0, so fixed change in time. Maybe I'm on the wrong layer. All right, so we have a fixed change in time every time we are moving into the future, a decade. Let's see, our change in branches, we go from 8 to 33. So what is that? That is plus 25 branches. Then we go from 33 to 128. Well, that's way more than 25 branches. That's going to be what? 5 less than 100. So that's going to be plus 95 branches. So this clearly is not a linear model. And so let's think in terms of an exponential model. How much do we have to multiply to go from, did I do that right? 128 minus, yeah, if it was 133, then it would be 100, and then it's 5 less than that. Yep, okay. So now let's think about it in terms of an exponential model. In terms of an exponential model, we care, well, what do we have to multiply for each step? So if we have a constant step in time, what do we multiply for how much we increase our branches? So to go to 8 to 33, that'll be approximately, it's going to be approximately 4. It's going to be a little bit more than 4. 33 to 128, well, that's going to be a little bit less than 4, but it's approximately 4. 33 times.
Here's an here's an expression that we could know. That is, it's approximately 4. It's approximately 4. So if you want to represent the meaning of approximately equal, then you use this sentence. It's approximately 4 or 3 or 5, whatever number you like. Okay. So that's today's learning, and inside of this video we have learned about what is exponential growth and what is exponential decay. To be honest, that's a quite a simple concept. For example, if you want to have an exponential growth, you would have x to the power of a number which is greater than 1. But if you want to have an exponential decay, you would have x to the power of a number that are less than 1. So do you get the idea of it? Oh, sorry, I probably did something wrong. That's not the case. The real case is that if you want to have a growth, exponential growth, you have to have a number that's greater than 1, and with the arbitrary power. This is your real number, the n times this stuff. And if you want to have an exponential decay, you would have an expression like this: n times a number that's less than 1 to an arbitrary power. Okay, I guess this is the correct way to represent what we have learned today. Alright, that's it. I hope you enjoyed this video, and I'll see you guys in the next one. Bye.